So let us begin. So once again, just a reminder that I won't be seeing your chat. So if you have any questions, please, or comments, just speak to the microphone. If you have any questions of personal nature, right, send me an email, okay? And I'll respond to it after class. So kind of reminding us, right, where we were. So basically last time, right, what we did was to establish, right, the foundation, right, of probability, if you will, or like the terminologies starting with sample space, right, and outcomes and events, right? And then we look at, basically rules of sets, right, like union, intersection, complement, right? And how basically, right, these operations interact with each other. The one thing, right, that would be used quite often for us is De Morgan's law, right, which says that the complement of the union is the intersection of a complement. And then, right, after we establish, right, basically so basically, right, you think about outcome is like the elements of a set, right, the sample space. The sample space is a big set in which outcomes, right, are elementary elements, right? And then events are subsets of that big set of the sample space. And so we talked about how, right, we can do set operation with events. But then, right, probability would be ways to assign, right, a value between 0 and 1 to an event, okay? That follows rules. What are those rules? Well, the rules, right, are as followed, right? The empty set has probability 0. The sample space has probability 1, right? The numbers that you assign must be between 0 and 1. And, right, maybe surprisingly or not, the only rules that you need to follow or stick to is that, right, if you have mutually exclusive events, then the probability of the union is the sum of the probabilities, okay? These are the only rules. But as you can see, right, as we have seen, many consequences can be drawn from these rules, okay? Not even least of all, is the general inclusion-exclusion formula, right? Again, these are all from like set theory and how, right, the set interacts with these assignments. And so some of the consequences, right, that we talked about last time, the complement has probability as 1 minus, right, the original probability. If a set is contained in another set or an event is contained in another event, then its probability cannot be more, right? And here we talked about how, right, E is contained in F. It's equivalent, right, in terms of logic to E implies F. And the general inclusion-exclusion formula, right, says that the probability of the union is the sum of the probability minus, right, the intersection. Again, right, seems simple, but I can tell you that inclusion-exclusion formula is the number one place that students make mistake in, okay? So pay attention to this. Not only because, right, it's simple, but we will pretty soon talk about, right, the general inclusion-exclusion formula for 3 sets and in general, right? So this is something you want to pay attention to. And in terms of problems, right, we looked at, some kind of like warm-up questions that talk about events and things like that, right? And then we looked at, right, this first problem, well, not first, but third problem, right, where we start to deal with, right, some rules of probabilities, right, and sets. But these are the answers, right, to the questions. So I guess let's continue with the problem set and let's continue to problem 4, okay? Again, right, these have to do with, I guess, inclusion, exclusion, or, rules of probabilities in general, right? But the point is for you to, right, with number 4 and moving forward, a lot of the problems that we'll be dealing with in this class will be, let's say, word problems in nature, right? And you will have to translate these word problems into probability language, right? And then apply the law correctly to solve these problems. So we'll give it like, 1 or 2 minutes for you to take a look at the question, the problem, and then I'll ask for, any input and we'll show you the solution. All right. So the first step, right, when you look at a word problem, is you should translate them into symbolic language, okay, before you even attempt to solve a problem like this. So, things like, denoting events, right, would be essential. So we have what kind of events here? We have the ring, right? A necklace, right? So let's say R is the event that student wear a ring. N, right, is the event that student wear a necklace, right? So that's just naming events. And then we have to set down, right, the given information. What are we given? 60%, right, wears neither a ring nor like necklace. So in terms of probability, right, what are we talking about here? Probability of what equals to 0.6? I guess I miss a dot here, right? Is there a dot here? Yeah, there's a dot. So the first statement, right, what kind of event is this in terms of R and N? Anyone? The sound is coming through, right? Just checking. Yeah.
It's the probability of not R and not C, or like the complement of both. Like intersection,
Yeah.
intersection
R
of
complement and complement, correct.
yes.
Good. What about this one? So I guess that's clear, right? P of R is 0.2, P of N is 0.3, right? So A asks for what? P of what? This is too easy. R union N, right? Which is what? What is the answer here?
0.4.
Reason is
I just used logic. I don't know.
well, okay, fine, but the I don't know is not very good, right? You should always be able to justify your answer. All right. So where does that come from? Huh?
De Morgan, the
Exactly, right?
yeah.
Correct. So if you look at, right, R union N complement, that's R complement N complement, correct? So this exactly is 1 minus P of R union N complement, right? Using that law. And De Morgan's law say, so this exactly is what you want to note. Right, it's 1 minus 0.6, and whatever that is, 0.4 is okay. All right. Okay. Now part B asks for P of Rn. So how do we do this?
Is R plus n minus the intersection?
Minus
The or of them, like
the union. Yeah, correct,
union.
right? Because we're dealing with the intersection. That's correct. Very good again, right? So this actually, right, notice that this is not directly given anywhere, but we have the inclusion exclusion principle, right? Which says P of R union N is P of R plus P of N minus P of Rn, which, right, comes to, right, if you put this on the opposite sides, gives you P of R plus P of N minus P of R union N, right? And this is just where it comes from. Plug in the numbers, will give you 0.2 plus 0.3, right? And then I guess we just found the answer in part A, right? So I guess now we can plug in 0.4 if you want. All right. Any question? Okay. So let's continue. Oh, by the way, right? You see a slide later on, but here I just want to comment a favorite thing for students to do. I don't know from where, is to do this. I guess 0.2 times 0.3, right? And that's wrong. Okay. If you ever even think of thought about this, just abandon it. It's just wrong, right? This habit is as bad as trying to say that the union is a sum, because it just comes from some kind of, you know, things that you tend to think of in general, but it's not true in general, right? Well, of course, right, this, the saying that union is a sum, right, is assuming that the events are mutually exclusive, which they don't have to be. This we haven't talked about, but I guess, you know, this, if you took some kind of elementary probability statistics, you would know where this comes from, right? This will assume that the events are independent, but, right, events don't have to be independent in general. So, right, if you want to do well on this course, in this course, right, you have to respect the laws, you have to respect the logic, right, and you have to know where the rules come from. Like doing things because it intuitively feels right, whatever that means, will land you in hot water very quickly. Is that okay? All right. Let's look, take a look at this question. All right. So again, right, we need to transcribe the information here into probabilistic language, right? And I guess here the word cigarettes and cigars are quite similar. So we're just not going to use the word C for it, right? We're going to call E as smoked cigarettes and F as smoking cigar, right? So what information are we given? 28 smoked cigarettes, right? So PE is 0.28. 7 smoked cigars, so PF is 0.7. Sorry, 0.07, right? And 5 smokes both, so PEF is 0.05, right? So A's asked for what? P of E complement F complement, right? And the answer here would be how will we do this?
You find the union of cigars and cigarettes.
Perfect, right? Exactly. So you need to do the Morgan's law again, right? So this is 1 minus P of, right, E union F complement because of the Morgan's law, right? And so, is that okay so far, this one? And so, right, we need to work on P of E union F first, right? So P of E union F is PE plus PF minus PEF, right? Which are given all in here. So 0.28 plus 0.07, right, minus 0.05. And by the way, right, I guess there's a complement here, right? So, well, you know what? I'm being silly, right? Why am I doing this? It's just this, right? Sorry. So there you go, right? So therefore, right, the answer here will be 1 minus P of E union F. So 1 minus this, whatever that is. Is that okay? Any question? All right. So what about B? Percentage that smoke cigars but not cigarettes, right? What are we asking for? P of E F complement, right? How do we do this?
Is it not the opposite? Since
Meaning?
it's not
Oh,
not
sorry.
cigarette
Sorry, did I read it wrong?
complement.
Yeah. Sorry. My notation, right? Yeah. Appreciate it. E complement F. Thank you. I got in terms of my notation, right? Yeah, absolutely. Yeah. So how do we do this? So here, right? This is not directly of some rules symbolically, but if you visualize things out, right? So E F, right? So where's E complement F? Well, E complement F is the part that's in F but not in E, correct? So right here, that's E complement F. But once you realize it that way, then clearly, right, it will be PF minus PEF, right? By the mutually exclusive principle. And then you just plug in. Any question? Okay. And that's the last question of problem set 1. All right. Any question in general before we continue with our material? All right. So right, as you can see, right, so far we've been using these rules, right, for problem set 1, and we did not touch I guess the more general, right, inclusion exclusion principle. We will soon, okay? But so for now, let's talk about this, and then you'll see how it's applied once we get through the combinatorics, I think, right? Yeah. So but so the whole point, right, is that a rule is not very good if you only limit it to like a certain specific case, right? For example, inclusion exclusion formula is not very good if somehow you can only apply it to a union of 2 sets, because right, we have union of 3 sets or union of right n sets in general. So we need to have that rule generalized, right? So the generalization of inclusion exclusion formula for 3 sets is the following, right? You add the probabilities, subtract the pairwise, and add the triple intersection. And this pattern, right, namely add, subtract, add, will be right the pattern for the general case. Okay, so pay attention to it. So the picture of it, right, is as followed. But this is where, for example, right, for those of you who kind of want to specialize more in math, you will quickly see that, right, this proof by picture is starting to get sort of not untrackable, but like harder to track. So let's see, right, with the proof by picture right here, it's quite simple because again, right, if you add this and this, you see you double add, right? So you double count these intersections, subtract it once to get the area of the 2 circles, right? But here, right, you see, okay, if you add this, this, and this, then you sort of overcount these regions, right? But how many times? Well, okay, right? So clearly you somehow double count this, so you subtract this, you double count this, you subtract this, you double count this, you subtract this. But then, right, it turns out that you over subtract this. So you add this once in, right? So by the way, right here, I took the picture from Wikipedia, they call it ABC, while I wrote this here as EFG, right? I guess it's the same thing. So hopefully you won't be confused by that. But the point is a proof by picture here, right? The picture is drawn for you just so you see. But proof by picture starts to be not quite helpful. All right. So that's why math is invented, because I mean, if you can always do everything by picture, we're not sitting here, right, talking about math. So while I'm not saying that you cannot really track it out by picture if you count this out correctly, yeah, right, with 3 sets, you can do it. But what about 10 sets? I don't think, right, anyone has the patience or even the ability to draw the intersection of 10 sets precisely, right? So we need some other ideas. And the idea, right, here to kind of get to the general case, whatever that number is by induction. Okay. And I'm just going to show you how to move from 2 sets to 3 sets, right? Meaning, assuming that this is true, we're going to show why this is true. And right, you can apply that to the general case by kind of rewriting it. But we're not going to get super focused on this. But how do we do induction here? Induction basically, right, is to use what you have proved for the, I guess the new case, right, the more complex case. So here, right, if we have P of E union F union G, what we can do is basically group, right? This is by associativity, right? But if you group sets like this, then suddenly you have two sets, right? So you can use you can use inclusion and exclusion formula for two sets here. So what happens here is this is going to be P of E union F plus P of G minus P of E union F intersect G, right? And this is it, because we look at this as a inclusion exclusion formula for two sets. All right. Now what can we do? Well, what we can do here is, right, this is clearly at the level of two sets, so we can apply the inclusion exclusion formula again, which is PE, right, plus PF. Let's put PG here as well. Right, which is exactly this. And now, of course, this will land us on a minus PEF, right, which is this guy. Well, but, right, of course, we still have this to deal with. And this, right, we will use the distributive law, right, which says this is P of EG union EFG, right? And so this again becomes the two set levels, right? So we can use inclusion exclusion formula with it again. So which will be, right, all these stuff are the same, right? So I'm not going to rewrite it. I'm just going to rewrite this part, right? This is going to be PEG plus PFG minus P of EFG, right? In parentheses, because this is this. And now if you distribute the minus in, you see that you pick up this term, and that term. So that finishes, right, the proof or the explanation, right, for inclusion exclusion formula at three set level. Any question about this? All right. So what is the inclusion exclusion formula in general? This is the general formula, right? And yes, you need to know this formula, right? There will be a problem or some problems in this class dealing with this. So what is it, right? So basically here, you don't have to specify what the number of sets that your union is. It's just some kind of union over some number of sets, right? The principle says that, it's very easy actually. You first add, right, all the sets at the single level. Then you subtract all the sets at the pairwise level. We'll explain this soon. Then you add all the sets at the triple level intersection. And you keep alternating the sign, right, until you reach the last layer, which is the all intersection, right, of all n sets. Now, how do you know what sign that goes in front of this? Well, right, you just observe. If you have one set, you have a plus. You have two sets, you have a minus. Three sets, you have a plus, right? So in general, it seems like it's not, it seems like it is, right? Minus one raised to the number of layers, right? The level layers, plus one, okay? So the last thing to explain, right, is what are these notations? These notations, right, is in contrast with, you might see something like this, I not equal to J. That's the contrast, right? I less than J versus I not equal to J. The contrast, as you'll see, right, is that the term here is, right, here order matters. And here order does not matter. Or more concretely, right, what goes on here? What goes on here, right, is that if you include E1, E2, then you will not include E2, E1, right, because 2 is not less than 1. Meaning if you have a pair of numbers, you only include it once. On the other hand, right here, if I is not equal to J, if you have E1, E2, you will also include E2, E1. Right, that's why you kind of over every pair, you do it twice, right? You'll see this very soon when we move on to the combinatorics, but that's the meaning, right? Same thing here, right? When we do I less than j less than k, what we mean is that we only do a triple once. For example, right, we only do 1, 4, and 5. That's it. We will not do 5, 4, and 1 because, right, the order won't satisfy this. But if you say something along the line of I not equal to j, not equal to k, then you will have to involve all triple 6 times. 6 coming from 3 factorials, right? Taking in all permutation, right, of that triple. Again, right, that's the idea from combinatorics, which we'll look at soon. But right, for now, right, the point is just that, right, here, very plain and simple. Every pair, every triple, or every, right, sequence is only done once for each of the choice. Right, so for example, here you see E1, E2 only done once. All right, any question about this? All right, so let us continue with the second lecture. All right. Hold on. Let me see here. In principle, I should have a slide to explain to you why. Yeah, here. Okay. Sorry. Let me. Yeah, I did not. So this is. I did not go to the last slide yet. So. Okay. So the next topic, right, that we'll talk about is combinatorics. But we want to explain to you why we, in any probability class, right, combinatorics is routinely incorporated into the materials, right? At least, for some lecture or so. The reason is as follows, right? So remember, right, we have a sample space, right? S, okay? And then we have outcomes, right? You think about it as elements of S. All right. And then you have E, right, which is a subset, right, which is an event. Okay. And of course, right, the question is about calculating probability of E, right? I guess no need to have too many question marks. So, well, how do we do this? Note, right, so far, okay, you should not get the impression that the probability is something, well, whatever, right? The point is, right, notice that the axioms of probabilities tells you that if you assign, right, a probability event, they must follow these rules, meaning that, right, you have to assign it in a rational way. But it never specifies exactly how you can specify probability of an event, right? As you probably can already have a feeling, right? For example, right? If you have a coin, right? If you have a coin toss, let me see where I can have. If you have a coin toss, right? The sample space is head and tail, right? Head or tail, whatever, right? Well, what probability can we assign here? Well, of course, the traditional way is 0.5, 0.5 for each, right? Which is a good way, but you don't have to, right? You can assign 0.4, 0.6, 0.9, 0.1, whatever, right? Of course, 0.5, 0.5, right, refers to the coin as fair, but you don't have to. Another example, of course, is the dice toss when you have 1 to 6, right? Again, right, traditionally you assign 1/6 each, in which case, right, you assume the dice is fair. You don't have to, right? You can assign any, right, set of numbers between 0 and 1 that add up to 1 and non-negative, right? So basically, right, the question is, okay, given a sample space and given, right, a set of outcomes, well, how do we assign probabilities? Or, you know, maybe put it a different way, right? How do we calculate probability of an event, right? For example, let's say you toss a fair dice, how you calculate probability of the dice roll even, right? Something like that. So here, right, the remark is like this. If all outcomes are equally likely, all right, and there are n outcomes in the sample space, meaning there are n items total here, then any event, right, that contains k outcomes will have probability k over n. Okay? Well, why is that? I think, right, the reasoning is clear. But basically, right, the reason is as follows, right? If there are n outcomes in the sample space, then the probability of an outcome, right, any outcome you want is what? So, okay, sorry, let me write like this, right? If there are n outcomes in the sample space, then you can denote the sample space like this: O1, O2, up to On, right? Where each of this is an outcome, right? Okay. Now, the outcomes, right, are equally likely. Sorry, the outcomes are mutually exclusive by definition. Sorry, right, mutually exclusive. Correct? Because they are elements, right? So the intersection of, we talked about this before, right? The intersection of sets of a single element by definition are empty, right? They have nothing in common. And so therefore, right, by the by the axioms of probability, right, then the probability of S being the union, right, of all these outcomes will be the sum, right, of the probability of the outcomes. All right, that's always true, right? This is true in general. Of course, right, the probability of S is 1 because that's the axiom of probability, right? So far, everything is just axioms. But now, right, suppose for some reason you know that all outcomes are equally likely. Okay. Again, right, like the coin toss or a dice toss where it's a fair coin or a fair dice. And all these guys are the same number. If they're all the same numbers, we just call it whatever, right? Little p, for example. Right? And of course, this is n times p. So little p is going to be 1 over n. Right? Meaning that each of the outcome has probability 1 over n. Right? 1/2 here and 1/6. Right? That's where we assign the probability from. Right? Okay. Now that's an outcome. But what about events? Well, events goes the same way, right? Suppose an event has 4 outcomes, say O1, O3, O5, and O6, right? Then what's PE? Well, clearly, right? PE is going to be a sum of the probabilities outcome because they're mutually exclusive again, right? But if each of this is 1 over n, then of course this is going to be 4 over n, right? So in general, if an event has k items, then the probability is k over n. So, right, all of these comes from the axiom of probability. Okay, so far, any question? All right. But so, right, what this means is that if you have a sample space where outcomes are equally likely, then, right, the calculation of probabilities come down to counting the size of the events and counting the size of S, the sample space, right? Here's an example, right? I mean, so far, the example we've done is easy, are easy. But let's say you roll 2 dice, right? Roll a fair dice twice. And you want to find the probability that the sum is 11, let's say. Well, if you think about it, right? This probability will be what? Will be how many pairs of numbers that add up to 11. I haven't looked at the count recently, so whatever that is, right? Just list it out. Over, right, the total number of pairs we have, which, right, if you know combinatorics, it'll be 36. So there you go, right? Here, I'm just demonstrating again, right, that in a sample space that's whose outcomes are equally likely, then what we actually do when we do probability are just counting. And so we need to know how to count quickly, right? Like this thing, like 6 squared, right? Which is the size of the sample space. This question mark, why do I put a question mark here? As you'll see that the number of pairs that sum up to 11 falls outside of basic rules of combinatorics, meaning that there's no quick way to do it. You just have to list things out and then count it. But what that means, right, is that still we need to know how to count things up quickly, right, to do probability. Again, right, in a sample space or in experiment where outcomes are equally likely. And this explains why we transition to combinatorics as the next materials that we'll be discussing. All right. Any question about this?
Professor? So, like, with these counting rules here, like, are they the same for finite outcomes and infinite outcomes?
Great question. So, basically, how to say this, right? These tend to apply to finite sample space, if that's what you're saying. It's not finite outcomes, right? Finite sample space. The reason, right, is here. We start out with, right, the sample space has size n. Where was it? And so this k over n, right? So if n equals to infinite, you already see what's going on, right? It boils down to 0, so even if you count, it doesn't really mean much. Or it doesn't really help you do the probability. Does it make sense? So yeah, the setup, as you see, tends to revolve around finite sample space. Okay, but
Okay.
I can imagine that once you understand this principle of counting, as you see, like basically we'll move on to other contexts where counting is still a sub part of what we do for other reasons, right? Not for assigning probability, but so short answers, you're right, but long answers, well, it depends, right? Combinatorics will still be relevant later on. But yeah, for the purpose that I'm advertising here, then you're correct. That finite sample space is where we apply it to. Does that answer your question?
Yep.
All right, cool. All right. And I think we talked about this, right? Basically, independence is not something we are dealing with right now. Don't assume it. Don't even think about it. We'll talk about it later, right? And it's not like we won't do independence in this class. But a very subtle thing that we will clarify in this class, right, is basically, for example, right, when anyone thinking of probably getting 2 heads, right, when you toss a coin twice, right, fair coin, everyone will say 1/4, right? Easy. But when asked for a reason, they will say, well, because it's 1/2 times 1/2. And this is wrong in principle. It's not wrong in the answer. Numerically, it's correct, but it's wrong in principle. And again, right, this probably is annoying to some of you, or most of you, who knows, because you just think that if you get the right answer, then who cares? Well, we do care because, right, the logic is 90% of it. It's wrong in principle in this way. When you say you toss a fair coin twice, no one says in that assumption that the tosses are independent. Well, I don't deny, right, that yes, independence is somewhere in there. But if you read the question very carefully, it never says that is independent. In fact, independence will be a consequence, right? It's a complex stuff. But what I'm saying, right, is that the 1/4 here for now doesn't come from 1/2 times 1/2. But the 1/4 here comes from what? Surprise, comes from counting. Why? Because if you toss a coin twice, what are the outcomes? Head, 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 tail, tail, head, tail, tail. And because the coin is fair, all of these are equally likely. Therefore, the probability of each of them is 1/4. So this comes from counting, not from independence. Is that okay? Yes, we will talk about independence later on, but when you do probability, right? What assumption you start with, draw into what consequences will be super important, and we need to respect that. And so, yeah, this is also in connection with counting. Any question? Okay, so, yep, this is truly the end of the slides. So let us move on to lecture 2. Okay, so now, right, that we have advertised for, right, why we want to do counting, right, in service to, you know, let's say computing probability, right? But of course, combinatorics is useful in of itself, right? And you, as I also mentioned, we will use combinatorics later on in this course in another context. But yeah, right. So basically, combinatorics, right, are techniques of counting. Of course, not basic in any way, but of course, that's referred to basic combinatorics, meaning that the things we'll be talking about are basics, right? We're not talking about advanced combinatorics. That's for a different course. So basically, what techniques are we looking at? We'll be looking at, roughly speaking, 3 techniques, but you know, there's some variations of them, right? The first one is the so-called multiplication principle, which basically looks at how different ways you can combine different lists, right? Why combine? Because you can think of, right, in the example we have here, we have appetizer as a list, you have main course as a list, and you have dessert as another list. Right? And you try to combine this by picking one item from each, right? So multiplication principle will allow you to calculate how that happens, or how many ways that can happen. And of course, right, the answer is already in the name, you multiply them out, right? But we'll explain. The second one, right, is permutation, right? Again, a very classic way, classic problem, right? Classic question. So if you have like n items, right, 1 to n, right, or you have n spots, let's say, right? Let's say you have 5 spots, if you will, and you have numbers from 1 to 5, right, like this. How many ways, right, can you write down this list, right? Of course, here order matters because you have a list, right, a sequence of numbers from 1 to n. So how many ways can you rearrange them, right? Again, right, I guess it's no secret, but the answer here is factorial. The answer is 3 times 6 times 5. Again, I'm just telling you the answer, but we'll talk about each of these in detail soon. Combination, okay? So combination is a number of ways to choose a subgroup out of a group, out of a big group, right? Where order does not matter. So basically, right, it tells you how many ways you can, right here, right, pick a group of 5 out of a group, let's say 44, right? Without caring how these 5 matters in terms of their role, right? So all these 5 play the same role in this group. A different variation, right, is when you took out a group of 5, or let's say a group of 3 here, but you assign them different roles, okay? Let's say one is a president, one is a VP, one is a secretary, okay? The reason, of course, right, you see, right, if you assign one of them a role for each of them, then who, right, among the 3 taking on which role will be a different count, right, a different way. So you have to look at the different permutation, right, in terms of their roles into account. So while these and these are connected, right, the answers are not the same. So these are, I guess, the ones I'm giving you here are, let's say, so-called classical questions, right, that can be asked in combinatorics. Again, right, of course, the actual questions, actual problems we'll be doing in this course will not be as simple as this, but we will have to build up, right, from the ground. So these are the main, the elementary, right, problems that are meant to illustrate the principle. All right, any question before we continue? Okay. So just kind of like, a heads up on, right, what you need to know or what you need to master, right, in a combinatorics problem. Well, the first thing is, of course, you need to know what principle to apply, right? If you read a problem and you have no idea if you should do combination, you should do multiplication, you should do permutation, well, I guess, right, you're lost. But having said that, right, that doesn't mean that you use a single principle and you can solve the problem, right? That's rarely the case, okay? You might have to combine different principles, okay, in a problem. So never expect that you can solve a problem using a single principle. It's just too easy, right? But beyond that, right, right, there might be problems where it's similar to what you've seen, but it's twisted in a way that you have to reinterpret the problem and apply. Basically, you have to modify the principle yourself, right? And the example I give here, right, is that instead of arrange items in a line, right, you arrange the items in a circle. Okay. And how many ways can you do that? Is there any difference? Intuitively, I hope you see that yes, there is a difference. What is the difference? We'll see, right? It's actually one of the problems we'll be considering soon. But clearly, right, arranging items in a circle is not, let's say, a principle listed here. All right, you can you can list a principle of counting items arranged in a circle, but then our list will never end, right? Because we just keep adding things in. So at some point, the list must end, and you have to, right, be kind of flexible, right, in applying your principle. Okay. All right. Yeah, this one right here is one of the, let's say, a more challenging problem, right, that we'll be dealing with soon. But yeah, right, these are meant to be, let's say, examples, right, of questions that are not directly easy, right, but needs to be kind of thought about, right, and then apply the combinatorics principle to solve, right? We'll be looking at a lot of these soon. Okay, but yeah, keep this in mind, right? I guess, long story short, combinatorics problems are not straightforward. You really have to work hard on it. All right, so I think we're approaching the time for the quiz. Let me give you the quiz, and all right, let's see here. So right here, let's do this one, okay? So just write down the answer for part A and part B, and we'll continue at 7:05. All right, and remember, you upload the answer to Canvas assignment. Today we still do not grade based on precision, but you should do it just in case, right? I mean, for practice. Friday, right, is when the quiz starts to count. Okay, but I will turn off the video and the sound, and we'll continue at 7:05. Okay. Any question before I turn off the sound and the video? All right. All right, let's continue. Any question before we continue? Okay. All right. So I guess, right, just to summarize, the message here, that basically, right, what we'll be discussing are, mm, 2 or 3 principles, okay, of combinatorics, as demonstrated by 2 or 3 simple problems. But the story does not end there at all, okay? Where the true challenge is where you have to look at, let's say, challenging problems where you have to see how you combine the principles or apply the principle in an appropriate way, right, to solve new problems. Of course, we'll be discussing those too, but that's the theme, right, of what's coming up next. Basic principles first, basic problems, and then how to, right, then the more advanced problems. All right. So the first, and let's say this is really the backbone of everything in some way, right? That if you have, right, n sets, and if you pick one item from each set, all right, then the number of different lists, right, with one item from each set is a product of the sizes of the set. Okay, that's it. Right, and if I want to tell you right here, the keyword is 1 from E1 and 1 from E2 and, right, so on, right? So the multiplication principle, not surprisingly, is connected with the word and. But of course, right, if you abuse this or you use it incorrectly, then it's not going to help. But, right, the word and is likely to be connected with, right, the multiplication principle. And of course, right, the other side of things is the word or, right? E1 or E2, and you can guess already, right? It will have to do with sum and subtraction, right? So sum and subtraction. This is the inclusion-exclusion formula, right? But the word and, right, will be involved with the multiplication principle. And so you have to, right, look at each problem cleverly sometimes to see what the sets are. But, right, sometimes it's just kind of pretty straightforward, right? How many ways to choose a meal, blah, blah, blah. Well, again, right, the answer hopefully is 3 times 6 times 5, right? No mystery here, okay? Any question? All right. So now, right, moving on to, right, the applications. Usually it's used to quickly count the number of, right, the number of outcomes in the sample space or the size of the sample space, right? And it usually comes as a power because you kind of repeat the experiment, right? If you toss a coin n times, how many outcomes are there? What's the size of the sample space?
A 2 to the n.
Correct, right? 2 times 2 times 2, n times. Okay. All right. So these two actually, right, are examples of kind of a more advanced application of a multiplication principle. But let's see here. Let's maybe tackle this first, right? And we'll look at the card later on. If you draw 3 balls, right, or 10 balls with different numbers without replacement, right? And here these terms will start coming in, right? Without replacement means you draw a ball, right? And then you keep it there and you draw it out again and again, right? You don't put it back. Okay. While with replacement, means that you draw a ball, right? And then you look at the result and you put it back before you sample again. All right. So again, right, this has just to do with like the number of possibilities or the sample space. So without replacement, how many, I don't know which one's easier, you pick, right? Without replacement, what's the size of sample space? And with replacement, what's the size of sample space?
Without replacement would be 10 times 9 times 8, I think.
That's correct.
And
Right,
then
yeah.
and then with replacement would just be 1,000, so 10 to the third.
Correct. So this is without, this is with. That's correct. And right, you can see this is exactly right an application of the multiplication principle, right? Because first draw you have 10, but then the second draw you only have 9 if you only took out one ball. And then third draw you only have 8, right? And then this is one ball from each turn, so it's n, so it's multiply. Similarly for 10 cubed. All right. Any question here? All right. Let's go back to this one, right? So we'll do a bunch of examples with cards. You know, it's just really the classical way to demonstrate combinatorics, right? Not because we want to endorse gambling or anything in this class, right? In fact, it's not endorsed. But right, if you are not familiar with a deck of cards, right, there are several things you want to pay attention to, right? A deck of cards has 52 cards in total, right? Consisting of, right, 4 suits, which are heart, diamond, spade, and heart, diamond, spade, and help me out here. What's the last one? Somehow I'm just blanking out. I can see the shape, but heart, diamond, spade, and club, right? Okay. And 13 denominations, right? Ace, which you can count as 1 or whatever, right? And then 2, 3, up to 10, and then jack, king, and queen, right? So basically, right, each of these denomination comes in 4 suits, right? Ace of heart, ace of diamonds, ace of spades, ace of club, jack of heart, jack of diamond, jack of spade, jack of club, that kind of thing. Is that okay? And of course, right, notice that 52 exactly is 13 times 4, right? Again, an application of the multiplication principle. Is it? Yeah, right. I don't know. It just seems obvious. No, it's not a multiplication principle. Sorry, it's just 13 times 4, right? Okay. All right. So what are we dealing with here? We want to draw a 5 cards from a deck of 52. So what is a sample space if we do not distinguish the suits? Or, you know, what about if we distinguish the suits? Whichever way you want to deal with first. And this question, right, before you give the answer, I just want to kind of tell you that this might be one of those so-called annoying factor of combinatorics, because depending on how you want to see the situation, the count will be different. All right, we'll talk about this in a different slide. But basically, right, this has to do with your perspective. Because I think a common question when it comes to this section in the probability classes, does order matters? Does this matter? Does that matter? The answer is I have no general answer for you, okay? A, it depends on the problem. You have to look at the problem and see if the problem requires you to do so. And B, sometimes it's up to you to choose whichever way, because in the end, when you compute the probability, it will come out to be the same answer for probability, not for counting. All right, we'll talk about that. But so, yeah, so the point here, I just want to acknowledge, or you want to note that depends on how you see things, the count may be different or will be different. That's just a fact of life, which will require you to be very clear, right, on what you are counting. It's on you, right? I'm counting this number because this is how I see things. And then, right, of course, given that context, you counted correctly or not. It's a different question. Well, does it mean that you can just do anything you want in a problem? No, right? A problem should be quite clear on, how you proceed with things. But like a lot of times you have two possible ways to do it, with or without order. Okay, we'll talk about later, which will lead to the same answer in terms of combinatorics, in terms of probability. But for now, right, let's just look at this one, right? So basically, right, why do we care about the suits here, right? So we want 5 cards of all different denominations, right? Meaning, right, let's say an ace, a jack, a 10, or a queen, right? But you see, clearly, when you say an ace, if you don't mention if it's ace of heart, ace of club, whatever, the count will be different, right? But meaning if you have 5 cards, let's say ace, 2, 3, 4, 5, right? That's 5 cards. But if you take into account that this is a heart, this is a spade, etc., right? Then intuitively, it's very clear that the count will be much more, correct? So yeah, let's see if you have an answer for this.
If we don't distinguish the suits, would it be 52 times 48 times 44 times 40 times 36?
I think no. That actually would be distinguishing the suit. But if you do not distinguish the suit, think about it. How many choices for the first card?
Oh,
13,
so
right?
52 times
No, not 52. Again, right? Do not, right? We do not distinguish the suit. Agree? That's what you're going for, right?
yeah.
So if you do not distinguish the suit, and then how many choices can the first card be? 1 out of the 13 denominations, not 52. When you say 52, you already take into account the suits. Do you
Oh,
agree?
okay. Yeah.
No,
that
again,
makes
it's very
sense.
subtle, right? It's very subtle, but yeah, right. That's that. And again, right? What's another clue? If you distinguish a suit, the count is much more, right? Than you do not distinguish a suit. And the way you're counting it is it's a pretty high number. So, all right. So if you do not distinguish a suit, right? The first card is 13. The second card is 12, 11, 10, and 9, right? This is not distinguishing. Agree? And now distinguishing the suit will be what you just said, right? 52, 48, 44, that kind of thing, right? But let me say this, right? Is there an easy way
Professor?
to write that? Yeah.
If we don't distinguish the suits, like
Yep.
after we pick a card, we could potentially get it again, right? Because we have like 3 other same cards then.
Yep, but you want all of different denominations.
I mean like when like it's not 13 times 12 times 11 times 10 times 9.
Why?
Because um like even if you like chose a card, it's not gone because you have 4 like 4 of the same type of card.
Uh-huh.
So like after you choose the first card, you could choose it again. So I feel like it
You're
um
thinking of something else. We're not sampling without replacement or something like this here, right? Or actually, here we're sampling. Correct. We're sampling with without replacement. You're correct, right? But we're just talking about denomination, clear and simple, right? For example, again, think what, right? I have 5 spots. Agree?
Hmm.
Well, if the first card is an ace, what choice can the second card be?
oh, I understand what you mean, but like, oh, I mean, like there still exists like it might be a spades ace or like a hearts ace. So I'm saying like the first card could be a spades ace and the second one could be a hearts ace.
Why do we care about that?
So then it would be like two aces.
Yeah, but we want different denominations, right?
I didn't understand different denominations.
Yeah, I mean denominations, right? Not different cards, different denominations. Is that okay?
Yeah, sorry. Yeah.
No, no worries, no worries. It's a term that maybe it's not you're not used to. Yeah, different denominations or different cards. All right. So right, but if we distinguish the suits, then how many ways? Like the other friend just said, right? 52, 48, 44, that kind of thing, right? What's an easy way to do that? I mean, what's an alternative way to do that? It'll be 13 times 12 times 11 times 10 times 9, and then all times 4 to the 5th. Right? Where does 4 to the 5th come from? For each of the denomination here would come in with 4 suits. Again, right? Nothing wrong with 52, 48, whatever. But I like this way of arranging things because I clearly distinguish denominations and suits. Any question?
If the order doesn't matter, would
Right.
you have
Good point. Good point. Right here, I implicitly order of the card matters. Yeah, sure. That's a good point. And that actually is another layer that if I put it in here, it'll be a way too, too many details. But yeah, when I do it like this, I distinguish the first card from the second card to a third card. You're right. You're absolutely right. If order does not matter, I have to divide it by 5 factorial. But I haven't looked at, permutation. So let's just keep things simple, right? Arranging in a sequence. Is that okay?
Yeah, thank you.
Sure. No, yeah, that's a great clarification. Absolutely. Here, that's implied, which I don't want to put in here because already, right, it's a little bit more detailed. Okay. So last one, right? And this is exactly dealing with orders. How many ways, right, can we arrange n items, n distinct items in a line? Well, I kind of give you the answer, right, as a hint, but can you explain why? Well, you think about it, right? If you have n items or n positions, right, n empty spots, and you put n letters into this, right? Well, how many choices can the first entry have? N choices, correct? And then the second one will have n minus 1 choices, n minus 2, right? So on so forth down to 2 and 1, right? And the multiplication principle says that you multiply these together because first spot and second spot and third spot, right, together be forming a list, correct? So therefore, the answer here will be n factorial. Okay, so far? Any question? All right. So, right, the point of these questions, right, besides, I guess, the first one, is that, well, none of these questions, let me say, are very simple. So if you find them difficult or struggle with the reasoning, etc., that's fine, right? Don't panic. On the other hand, if you don't find the reasoning very, very smooth, you want to go back, repeat the reasoning, right, and practice again until it sinks in, all right? But yeah, the point here, right, is that I want to demonstrate that the multiplication principle is almost like the mother of them all, right? Of course, it's an exaggeration. That's not true, right? There's some things that cannot be drawn from the multiplication principle, but it's used a lot, right? Of course, some of these can be done in of itself, meaning that eventually we'll just say n factorial without invoking the multiplication principle. But you can do a lot of things with the multiplication principle, right? So that's the first point. The second point, right, is actually that already you see the flavor of combinatorics, right? And that's why combinatorics problems are notoriously, let's say, challenging to students, because there's just a lot of details you have to keep track of, right? Or a lot of layers. What do you distinguish, right? Even the names of what you're counting might be confusing, which I completely, right, acknowledge if you don't, deal with this too often. But also, right, other things, for example, right, there's order matters. And here, right, you see, coming back to here, right, when I do this, what I did is I'd say the first card, second card, third card, fifth card, that kind of thing. So I have positions laying out for the card. But this may or may not be what you have in mind when you draw 5 cards, right? If you think about the natural way we draw 5 cards out of a deck, we just have 5 cards. We don't care which one is the first card, which one is the second card, etc. So in just to kind of explain what your friend was asking, this could be overcounting if, right, we don't care for the order of the card. So if that's the case, if that's what you have in mind, that order does not matter, then you have to divide by 5 factorial to account for, that order does not matter. Where does 5 factorial come from? Well, it comes from exactly, the permutation principle. All right. So again, right, does order matter here or not? And that's why I said I did not specify it here, because if I do, it just makes the problem a bit too long. So either way is fine, right? As far as the spirit of the question is concerned, and we'll explain more about that. But yeah, right, that's yet another layer. One last layer, right, is that it's just certain kind of words, if you change it a little bit, it'll become different. The word distinct here, right? You might think that means nothing. It means a lot, right? Here, think about it, right? How many ways can you arrange 3 items in 3 spots? You would say 3 factorial, right? Not true if the items are not distinct. For example, if you have 2 items that are the same, how many ways can you arrange this so-called 3 items in 3 spots? Where order matters, okay? But of course, if you permute the A's among themselves, you don't see anything because A is A, right? So this demonstrates that items have to be distinct. If items are not distinct, sure, you can still arrange them in a line, but the number of ways will not be n factorial. All right, we'll talk about this later. But this is yet a variation of non-distinct, for example, right? So many layers of details that I guess that's really it, for elementary combinatorics, but you have to keep track of these things, right? Distinct items are non-distinct. Does order matters or not? Again, that one will explain, right? And I guess what are we counting? All right, any question? All So, right, just kind of repeating what we just said. The number of ways to arrange any string items in a line is n factorial, right? Again, in a straight line, right? In a circle, it'll be different. Yeah, there you go. So, having known that there are n ways, n factorial ways to arrange n items in a line, how many ways can you arrange them in a circle?
N minus 1 factorial.
That's correct. But the challenge here is to explain your reasoning. Why?
Well, I think you need to place the first item so that you can establish the orientation. Like
Perfect.
otherwise it will like you can spin
Yeah.
a circle.
Absolutely. Everything you said is just right on, spot on. Yeah, very good. Right. So what's the distinction between arranging items in a line, right, versus a circle, right? Here's a line, right? 1, 2, 3, and I guess let's say 3, 1, 2, right, are two different, right, lists. But if you arrange them in a circle, right, 1, 2, and 3, right, then you see, right, 1, 2, 3, or 3, 1, 2. I guess 1, 2, 3, right? Or 2, 3, 1, or 3, 1, 2, right? Are the same, right? On a circle. Correct? And why? Why is, two ways you can see it, right? You can see that either you need to take out one item, right? To establish orientation. Because once you put this guy in, then whether you put 1, 2 in here or, sorry, 2, 3 in here or like this, right? These are different, correct? So as long as you fix the first item, then everything else can be arranged along a line. So that's why it's n minus 1 factorial. That's what your friend said, right? Take out one of them to establish an orientation. I think your friend also refers to another one where, right, if you note, right, that in a circle, if you rotate, right, the same orientation around, then you get the same permutation. But how many rotation can you do? Well, clearly you can do n rotations, right? Rotation of n items, correct? You can rotate it n times and still get the same permutation. That means from a line, you overcount it n times. So that's n minus 1 factorial. So whichever way you prefer, right? These are two different explanations, but they get to the same answer. Okay. Any question? All right. So, right, this problem, right, and the next one, the couple one, right, demonstrates exactly, combinatorics, right? I've got this asked to me. The students keep asking me these questions, like, I don't know, a lot of times. How do they study combinatorics? Or what's a good way to study combinatorics? The answer, and I guess some of you guys are already kind of having that question in mind. The answer is I don't know. Okay, I honestly don't know. The reason is, as you can see, right, you have to be able to visualize the counting in your mind. That's the best way I can tell you, right? The ones who visualize the counting correctly will count correctly. The ones who don't have a picture in their mind will never count anything correctly. That's all I can tell you. Well, how do you get to visualize stuff? No idea, right? A lot of practice. I struggled once in my life as well, right? So I freely acknowledge that these are not easy, but you have to practice if you want to get these things down. The more you look at the problems, right, the more you see how ideas are done, hopefully the more you sort of build up some intuition, some visualization or something. But I think as far as I'm concerned, or as far as I see how people do things, the people who can count have a picture in their mind. The people who can't, have no picture in their mind. All right. So as you'll see a lot when we deal with combinatorics in this course, I'll try to draw you some pictures, right? Explain to you how the counting goes. But of course, with a new problem will come a new picture. So, you just have to do one for your own, right? If you have a new problem. All right, so let's look at this one. How many ways can we arrange 5 couples in a straight line if the couples are to be together?
Well, I first kind of thought about the couples just together without like thinking about the couples themselves. So that would be
Yep.
5 factorial. And
Good,
then
yep.
I first just thought about like one of the couples, there's like 2 options per couple, kind of like in every one of those 5 factorial
Mhm.
arrangements. But then you also have like 5 couples themselves. So that would be like the multi-principal we talked about before. So I think it would be 5 factorial times 2 to the 5 for like the 5 different couples.
Perfect. Yeah, you explained everything correctly. Yep, very good. Right, so there you go, right? Again, right? So the visualization is, right, as I draw onto you here. First, you think of each couple as a unit, right? And you move the units around because they have to be together. That's why the 2 people in a couple becomes a unit, right? Become a unit. So there's 5 factorial ways to move these 5 units around to satisfy the requirement that the couple stay together. But then, right, do not forget that within that unit, the couples can, right, permute, right? Like here, right? For example, you can have A1, A2 or C2, C1. So there are 2 ways, right, for each unit to appear, right? And so taking that into account, there's 2 to the 5th ways to permute, right? The couples within each unit times 5 factorial. All right, any question? Okay, let's see here. So the next one is combination. I think we can do some problems first before we go to that one. All right, so let's take a look at this first question, and then I'll ask for your input on it. All right. So hopefully this is easy, just the first one. What's the answer to A? I guess not too easy, huh?
So for like the math one, I think it would be 6 times 5, and then you kind of just possibly have to multiply that for all the other ones. So maybe 6 times 5, then 7 times 6, then 4 times 3.
Okay, but what do you do with those numbers?
You multiply them all. Wait, hold on.
All right.
Oh
You have to
wait.
divide by 2, I think.
So, well, we'll get there, right? So dividing by 2, okay, I guess, sure. So maybe I should cover the, hold on. You know what? I think I should cover a combinatorics thing first because otherwise, yeah, this is awkward because of the order. But maybe I'm a bit too hasty. Let me see here. Yeah, sorry. I'm a bit too hasty to even jump to this question. Let me cover the combinatorics first. But right to maybe just to address the part where someone suggests you multiply these together, right? Is that
I was
what's supposed to? Yeah.
I was thinking adding them.
Yep, correct, right? This is add.
Okay.
But yeah, there's going to be some sort of divided by two. We're going to go back to this, right? I think I'm a little bit too hasty when moving this. But yeah, I just want to clarify, right? This is an add. Why? Because, right, it's either two from math or two from science or two from economics, right? So that's not all out multiplication principle, right? That's a or, so which is adding, right? But I think I'm moving a bit quick here. I think we need to talk about combination numbers first, which explain the division by two. All right, I apologize. I thought we've done enough, but let's go back.
I have a quick question.
Go ahead. Yep.
How would it look if it was 2 books from each subject? Would that be
Right.
multiplication?
So yeah, if it's two books from different subjects, it's going to be 7 times 6 times 7 plus 7 times 4 plus 6 times 4. Because you pick one from math and one from science, right? One from math and one from economics and one from science, one from, oh, sorry, math and economics here and science and economics. Yeah. So B is that. Correct. So B is straightforwardly multiplication principle. A, you need to kind of look at the combinatorics combination number first. Right. So this is math science.
No, I meant for the first one, you know how we said it's addition instead of multiplication. I was curious if you were getting 2 books from like each subject, would you multiply them together then? So
Sorry,
like two math books, 2 science books, and 2 economics books.
wait. What is the statement?
So I was
2 books.
asking, yeah,
Yeah.
so 2 books from each subject. So like 2 math books, 2 science books, and 2 economics books.
You mean 6 books total?
Yeah, and 2 each. Would you multiply them in that scenario?
You mean the students want to sell 6 books, right? Instead of 2, you want to sell
Yeah.
6 books.
Mm-hmm.
Where they want 2 from each subject. Is that what
Yeah.
you're saying?
Mm-hmm.
Let me think here. You want so you want 2 books from math, and then 2 books from, and then 2 books from. Yeah, that's correct. So you would multiply these numbers together, but in between
Yeah.
they're still divided by 2. That's correct. But that would be 6
Okay.
books, not 2 books. Yeah, that's correct. Yeah,
Wait, I don't understand where the divide by 2 comes from here.
I haven't covered yet, and that's exactly the combination numbers. Division by 2 is because you don't want to distinguish the order between the 2 books.
Ah, okay.
Yeah, I haven't covered it. That's why I say I'm going a bit quick. The answer, right, is 6 choose 2, which is the combination number, and you'll see it's going to be exactly these numbers right here. So I'm moving a bit ahead of myself. But the reason, right, is because when you sell 2 books, you're not going to say this is the first book on math, second book's on math, right? You naturally just say these are 2 books on math. Does that make sense? So yeah, yeah. So that's the answer. But I haven't covered the combination numbers, so let me go back and do that, and then we're going to revisit this. All right. Any question on this before I go back? All right. So, yep. Let's look at the combination numbers. Right. So the combination number, right? Exactly. Kind of, I think we're kind of dabbling into it. There's a number of ways to select k items out of a set of n items. where no order, right, is among these items. All right. So the explanation, right, is as follows. So basically, right, if you have n items, right, n items total, and so this is just an explanation on why, right? The number of ways is this, right? It's called n choose k. It's a notation. N factorial, k factorial, n minus k factorial. So I guess let's first demonstrate to you the example in the previous one, right? So remember, for example, right? I think there's 6 books on math, right? Let's say, and you want to choose 2 books out of it, right? So the notation here, according to this, will be six choose 2, right? You want to choose 6 books. Sorry, you want to choose 2 books, right, out of 6 math. And let's look at this, right? It's 6 factorial over 2 factorial, right? And then 4 factorial. All right. But what is 6 factorial over 4 factorial? That will be 6 times 5, right, over 2. And this is why, right? You see, we had to do divide by 2 when we looked at the number of ways we can pick 2 math books out of the 6 math books, right? If you don't divide by 2, right, what happens is, what you're saying is, well, I have 2 spots here. The first spot has 6 choices. The second spot has 5 choices. So together I have 6 times 5 choices to pick 2 items out of 6 items. But because you mentioned that this is first item and second items, you build the order into your list by that. Does that make sense? So that's why it's, when you do the multiplication principle as in a list and you divide it by, let's say, k factorial, right here, you kind of take care of the order. You take the order out of the count. Does that make sense? All right. So this is just, kind of some other explanation on what I just said. So you can take a look at it. But so maybe, right, let's do this and then we'll go back to the problem. So there are certain kind of properties about combination numbers you want to know, right? The first thing is that, right, choosing k out of n is the same as choosing n minus k out of n. I mean, in terms of the number of ways, right? Now, why is this true? First, right, you can see that both of them come out to be n factorial over k factorial and minus k factorial, right? So in terms of the formula, is symmetric. But there's an easier explanation, right? If you choose k items out of n items, right, it's equivalent to choosing n minus k items to remain in the group. You understand? So it's like a complementary way to look at it, right? If I want to choose 5 students, right, in the class to do something with me, it's the same as choosing the remaining students in the class to stay behind, right? So that's exactly that principle, right? So here, 6 choose 2 will be equal to 6 choose 4. Okay. So choosing 2 books to sell is the same as choosing 4 books not to sell. I mean, in terms of the number of ways, right? All right. And this binomial theorem will show up a lot in our class, so pay attention to it, right? This is called the binomial expansion, which I think, right, you guys should be familiar with the version of x plus y squared, right? And then the cube version. Right? So the coefficient is 1, 2, 1, and then 1, 3, 3, 1, right? Which is the Pascal triangle here, which we'll take a look at, right? Next lecture. But the point is, right, in general, this is the expansion, right? Meaning that you run through all the combination, right? For x raised to a power and y raised to n minus a power. But the coefficient in front of those combination will be n choose k. All right. Now, why is this the case? This is the case, right? Because if you look at the expansion, right, like this, well, how do you expand this this expression? Well, you expand it by distribution, right? But how do you distribute? Well, you distribute by, right, let's say pick an item here, and pick an item here, and pick an item here, right? Like that, until you exhaust all combinations. But for example, right, how do you pick an items here, an item there, an item there? What you end up doing is you pick, right, let's say, right, 3 y's or k, or you end up picking, let's say, k x's from n items. And then you pick the remaining, right, n minus k y's from the remaining items. So the number of ways you can do that, right? Let's say the number of ways you can pick 3 x's out of these things is n choose 3, and then n choose 4, and n choose 5, that kind of thing. Do you understand? So that's why, right? If you look at how you distribute these items out and then, you know, add them up, that's exactly this number. All right, any question? Okay, so now going back to, right, the problem set here, right? So the correct answer, or the easy answer to part A would be 6 choose 2 plus 7 choose 2 plus 4 choose 2. But, you know, it will coincide with this as well. Are we okay with this? All right. So I think we have space for one more question before we're done for the day. So, this is maybe not easy, but let's see, right? Let's see if we can squeeze it in. Maybe let's look at A first and see if you can do that, and we'll look at B. All right, any answer for A?
I think it's 8 choose 5 over 6 choose 3.
No. We're not doing any probability here. We're doing combinatorics, so any
Oh,
deviation is.
no, I'm just because I'm thinking like I'm just first calculating all of the like situations like without considering the feuding, and
Yeah.
then you have to remove
Yeah, but you're not gonna remove this by
so it's
division.
minus. Sorry, it's minus.
A choose 5 minus what?
Minus 6 choose 3 because I'm just removing the situation where the 2 people are already like definitely going.
Okay, no, that's excellent. So this is counting by complement. Let's see if the logic works, right? So A choose 5, right, are the number of ways you can choose everyone, right, to attend the party, regardless of the friends are there or not, right? So that's A choose 5. But now you want them to not attend together. Well, what's a good way to do that? Well, that means, right, you just kind of look at all the ways, subtracting the ways that they will attend together, right? You will get the ways that do not attend together. But how many ways can the two friends attend together? Well, right, if they already attend together, then they already show up in the party, right? So here's a party of 5, right? So if the friends attend together, they're already there, correct? So the 2 of them are already there. That means that you only have how many choices left? 3 choices, correct? But how many, you choose these 3 out of how many? Well, these 2 friends are already attending together, so you're not even choosing them out of this 8, right? You choose, yeah. So I mean, so the number of remaining choices you will make it out of 6. Does that make sense? So this is really 8 minus 2, choose 5 minus 2, if you will, because the 2 are already kind of fixed. So yes, this is the correct answer. All right, I know we already are out of time, but this is one way, right? Can we do it using a direct count? Is that possible? So here's a direct count, right? And you don't have to do it both ways, but so this is counting by complement. What's a direct count? Direct count is, right, well, they will not attend together, right? What does that mean? Well, they can either not attending at all, right? That's or only one of them will attend, right? So that will be how many ways if they if you want them to not attend together, right? So here, you either not invite both feuding friends or just one among the 2 friends to invite, right? Out of 6 friends, which is right a minus 2, you choose 5 because right you don't invite any of them to the party, or right you just invite one of them to the party. Does that make sense? And then right, of course, you can choose which one to invite, right? Or this is the complementary. So you can check that these 2 numbers are equal. All right. And again, of course, you only need to do one answer. You don't have to do both answers here. But this is hopefully showing you, right, that a problem can be approached in multiple ways. All right. So I know I'm a little bit over time, but let's stop here today. All right. We'll continue on Friday.
Have a good one.
Yeah, you too.